Hi everyone, welcome to your lesson. It's part of week 9, day 2 of your online learning for higher chemistry. So what we're going to do today is finish the chemical energy topic that we've been working on. And as part of that, we need to have a look at Hess's Law in a little bit more detail than what we did last day. Okay, so last day we had an introduction to Hess's Law, where we're going to add a calculation using the principles of Hess's Law. So as you're working through this video, make sure you've got your notes jotter handy so you can pause the video while you're taking down notes, and then just work through it at your own pace. If you need to go back, you can rewind the video, play something again, and just take your time to make sense of the examples that we go through in the video today. Okay, so learning outcomes that we're going to cover today. So these are in your Unit 3B booklet as part of the chemical energy topic within the booklet. And we saw these learning outcomes in our previous lesson because we got an introduction to Hess's Law. We learned what it was, and we saw kind of one aspect of how it can be used to work out enthalpy change. But as I said, we're going to explore that a little bit more today. So we're adding to what we already know about Hess's Law. Okay, so just a little reminder before we start looking at these calculations. There's no need to write this down because we did this last day. But the principle of Hess's Law is that when we look at a chemical reaction, no matter what route you take for the reaction, so whether you do the reaction in one step, what we would call a direct route, straight from A to B, or whether we have a kind of intermediate step in between, if we're getting from one chemical to another chemical, the enthalpy change for that reaction is going to be exactly the same, regardless of how we get there. So it doesn't matter how many steps there are, what kind of intermediate chemicals are involved. If we're starting with A and we're ending with B, regardless of how we get there, the enthalpy change is the same. So we used this principle last day, looking at diagrams like this one, to do fairly simple calculations using this principle. So being able to work out a kind of missing part of this sort of diagram. What we're going to look at today is still using the same principle of Hess's Law, but to do a more complex calculation. Okay, so I'm just going to kind of talk you through what the kind of reasoning behind this calculation is before we start. So all of this in italics, you don't need to take any notes just yet, but just to explain what we're about to do. So if we have a chemical reaction, so we've got a balanced equation for a reaction, but we need to work out the enthalpy change. And we maybe don't have, a particular pathway or route that we can take, like in the diagrams, to do it in a slightly different way. What we can do in that situation is we can think about the chemicals involved in our unknown reaction, and we can think about other reactions they take part in that we do know the enthalpy change for. So if we have something like carbon as part of our reaction, then we could think about a reaction where we're looking at the combustion of carbon. So enthalpy of combustion and combustion reactions are ones that we talked about earlier in the topic, and these are ones which are fairly straightforward for us to measure the enthalpy change for. So if we have carbon or hydrogen or a hydrocarbon, these are all things that we can measure the enthalpy of combustion for, and we can write equations for that, and we have delta H enthalpy change values known for those reactions. So if we think about our unknown reaction, we can use other reactions that those chemicals are part of. Maybe they're reactants in it, or maybe they're products. And as long as we have equations where we've got all the chemicals present in our unknown reaction involved, and we know the delta H values for those equations, then we can kind of manipulate those equations in order to work out the enthalpy change for the unknown one. That's essentially what we're doing here. So we have this kind of terminology we use for the reaction we're trying to work out the enthalpy change of. We usually call it the target equation. And what we try and do is we use other equations to construct that target equation. And those other equations involve the same kinds of chemicals. So you'll see when we go to the questions what this actually means, but just to have a think about it first before we start. Okay, so when we're trying to construct our target equation, what we're ultimately trying to do is work out the enthalpy change. So we're going to, at the very end of our calculation, add together all the enthalpy changes for the reactions that we've used to make our target equation. So all those other equations that we've used. But when we're trying to construct the target equation, what we will find is maybe a chemical is going to be on the wrong side of the equation. So we might need it on the product side, but it's on the reactant side. Or maybe we need 2 moles of a chemical and there's only 1 mole of it in the equation that we're working with. So when we're trying to construct our target equation, we're going to have to make changes to the equations that we're using. And the kind of principle of all this, the way that our calculation is actually going to work, according to Hess's law, and kind of keeping that principle in mind, whatever we do to an equation, we also have to do to the delta H value. So if we are multiplying an equation, do the same to the delta H. Or if we're reversing an equation, we do the same to the delta H. So as long as we remember those principles, that we change an equation and do the same to the delta H, and as long as we're careful to make sure that we get exactly the target equation that we're looking for, then we'll get the correct enthalpy change for that reaction. Okay, so as I said, it'll make more sense when we actually see the examples we're working through, but just so that you've got an idea of what's behind the calculations we do, if you take a wee note of kind of the changes that we're going to make in these calculations. So 2 ways that we can change equations when we're constructing our target equation. We can reverse the equation, so turning products into reactants and vice versa. And we can multiply the equation, so times by 2 or times by 3, depending on the number of moles we're looking for. And the main thing to remember is that whatever change we make to an equation, we're going to do exactly the same to the delta H value for that equation. Okay, so let's take a look at how this sort of question appears when we see it in an exam. So we've got an equation given to us in the question. There's actually lots of equations, but the first one is the important one up here, first of all. So we've got CH4 plus H2O changing into CO plus 3H2, sorry. And the question will say something like this. So it says, use the data below, i.e. these equations and these delta H values, to calculate the enthalpy change in kilojoules per mole for the above reaction. So we're getting a lot of information in the question. This equation that hasn't got a delta H value, this is the equation we want to work out, the delta H for. And the question has given us the equations involving these chemicals that we're going to be able to manipulate to help us do that. And it's given us their delta H values. Now this will usually be the case when you're looking at past paper questions and the examples that we're going to work through. In some older style questions from previous years of the higher course, you might see some questions where they don't give you the equations that you need to use to get the target equation. But those are not really the kinds of questions that you're going to see. So if you see a question like that, you can give it a try, but don't worry about trying to answer it, because it's not, you will get a question that's like this if this is something that you were asked to do. Okay, so let's kind of see where we are with the information that we've got before we start doing anything. So thinking back to the terminology in the previous slides, this equation up here, let's refer to this as our target equation. So this is the equation that we want to work out the delta H for. And we've got 3 equations to help us do that. So let's just label these as equations 1, 2, and 3. Okay, so this is just to help us kind of keep ourselves right with all the data and all the information we've been given. Okay, so as we've talked about, what we need to try and do is we need to construct the target equation. So we want to build this equation up here, build that equation from these other 3 equations that we've been given. And what you will notice with the equations that they've given us is that all the substances in the target equation appear in at least one of these equations. So CH4 appears down here in equation 3. H2O appears in a couple of different equations, and so on. So this will always happen when you get given data in the question. All of the chemicals in your target equation will be somewhere within the equations you've been given. What you'll also notice is that there will be some extra chemicals there. So in this case, I've got oxygen in equation 1 and equation 2, and nowhere in the target equation does oxygen appear. And the same thing happens with CO2. That's in a couple of our equations and it's not in the target. So that is normal. That's going to happen with the equations that we're using in our calculation. Don't worry about it. And we're not going to focus on these chemicals, because if we focus on the chemicals that are in our target equation, as long as we do what we need to in order to get those chemicals in the right place and the right number of moles, what you'll find is any extra chemicals like oxygen or CO2, they're going to sort themselves out. They're going to cancel out and essentially disappear from the equations once we finish doing all our manipulations. So don't worry about those extra ones, because we'll see how we get rid of them in the process. Okay, so we are manipulating our equations. So we're going to focus on which chemicals in the equation are part of the target and what do we need to do, where do we need to get them, how many moles do we need. And once we've done all of that, we're going to make the same changes to our delta H values, and at the very end we can sum up our delta H values to work out the delta H of the target equation. Okay, so in our working, what we're going to do is look through each of our equations and see which of the chemicals in the target equation they've got. So in equation 1, right at the start here, we've got carbon monoxide, CO, which is part of our target equation. Okay, that's the only chemical here that's part of this equation. But the CO in the target equation is on the product side, and we've got it in equation 1 on the reactant side. So what we're going to have to do with this equation is we're going to have to reverse it. So we're going to have to flip the equation round so that we get the CO and the half O2 on the product side and the CO2 on the reactant side. So while we're looking through these equations, it's quite a good idea to kind of jot down in your working what your plan is to do with each of the equations. Because we'll do this in the next slide, but just for now, let's just note down we're going to reverse this equation around. Okay, and when we do that, we're going to reverse the sign of the delta H. Okay, so negative becomes positive. So then moving to equation 2, we have got H2, which is in our equation, our target equation. Now we've also got H2O, which is in the target equation. But what you'll also notice if we just skip ahead to equation 3 is H2O appears in this equation as well. So sometimes you'll find this, that chemicals in your target equation appear more than once. What that means is that chemical is not our main priority. When we're trying to manipulate equation 2, hydrogen, H2, only appears in equation 2. So our only option for getting these 3 moles of H2 on the right hand side is doing it from equation 2. That's going to mean that we're going to end up with 3 moles of water, which is not what we want from the target equation. But because we've got water somewhere else, what we should find is that the water will sort itself out once we've finished our manipulations. So sometimes you have to make this decision. There might be a priority chemical in your equation. In this case, that's the hydrogen for us. So this is our only option for hydrogen. So the water is just going to end up wherever it ends up from this equation, but we will fix it with the next one. So with equation 2, to get our 3 moles of hydrogen on the right hand side, we are going to have to reverse this equation, and we're also going to have to multiply it by 3 so that we get 3 moles of H2. And when we're multiplying by 3, we're doing that with every formula in the equation. Okay, and we'll do the same thing. We're going to reverse the sign of delta H, and we're going to times that by 3. Okay, now last equation that we've got, equation 3, the chemical that appears here is CH4, methane, and the 2H2O that we already talked about. So again, water is not really our priority. It's going to sort itself out if we deal with everything else. Our priority here has to be CH4 because this is the only where the CH4 appears. So we are going to need 1 mole of CH4 on the left of our target equation. And that's what we already have with equation 3. So actually, we're going to leave equation 3 exactly as it appears. We're not going to multiply it, we're not going to reverse it, we're just going to leave it as it is because it's got CH4 exactly where we want it. Okay, so now that we've looked at our equations and we've thought about how we're going to change them and how we're going to change the delta H values with them, then as the next, or really the first bit of our working, our main working, is writing out these changes that we've made. So we're going to take each of our equations and rewrite them with the changes that we've made and recalculate the delta H values. And what we're going to aim to do here when we've got these equations all written is we're going to double check that we've done this properly. So if we have done it properly, everything should cancel out of all 3 equations. If we were to add them all together into one, everything should cancel out except for our target equation. So let's see if that's worked. So up at the top here, I've just changed these equations to reflect the changes that we said we're going to make. So I've now reversed equation 1, and I've done the same thing. This is now positive 283. Same thing with the delta H. I have reversed equation 2, and I've also multiplied it by 3. And I've done the same thing with the delta H. So this is now a positive value, and it's multiplied by 3. And then equation 3, we were just going to leave as it is. So I've not made any changes to that equation or the delta H. So if we look through our equations, so we're looking here to combine everything into one equation. So we want to check that anything that doesn't appear in our target equation actually cancels out. So CO2, right up the top here. If we scan down the rest of our equations, we've got CO2 on the left-hand side in equation 1, and we've got CO2 on the right-hand side in equation 3. So those two are going to cancel each other out, and that gets rid of the CO2, which we didn't need in our target equation. Okay. The next thing that we have in equation 1 is we've got half O2. Now, if you're looking over to the left-hand side to see what oxygen's over there, you'll see there's 2 moles of oxygen. So that's not going to cancel with just the half O2. But what we've got in equation 2 is we've got 1.5 O2. So all together, putting these two together, we've got 2 moles of oxygen on the right. So that means, in total, that's going to cancel out the 2 moles of oxygen on the left of our equation. Okay, and then everything else that we're left with is part of our equation, but the only issue we have is how much water is involved. So we've got 3H2O on the left, and we've got 2H2O on the right over here. What we're looking for is 1H2O on the left, which, if we cancel down, that 3 is going to cancel out the 2 waters over here entirely, so there'll be no water on the right, and then that is just going to leave us with 1H2O on the left-hand side. So now we've got H2O on the left-hand side, we've got CH4 on the left-hand side, we've got CO on the right, and we've got 3H2 on the right. So what we now know, having checked everything cancels out, is that we've manipulated our equations correctly. So we know that we're only left now with our target equation, all the chemicals we needed, the right numbers of moles on the right side of the equation, or the correct side of the equation. So that means we've done our calculation correctly, and we can now finish it off by working out the delta H value. Using the delta H values for the other equations that we've manipulated to reflect the changes that we made to get to the target equation. Okay, so just a case of adding them all together. Obviously, taking account of where you've got negative numbers that you're adding. So to get the delta H for our target equation, we're just going to sum up all of these delta H values. So plus 283 plus 726 plus the minus 803 gives us a final answer of 206 kilojoules per mole. Okay, so we started by looking at the equations in the question and figuring out how we were going to manipulate them to get our chemicals on the correct side of the equation for the target and the correct numbers of moles. We then made those changes to the 3 equations, and we made sure that we updated the delta H values to reflect that. So doing the same to the delta H as what we did to the equations. And then once we'd confirmed that we'd done that correctly by checking that everything else cancelled out of the equations, then at the very end we summed up the delta H values. So those are the kind of main stages of the process that you're going through. Okay, now these calculations do look quite complicated to start with because you're working with lots of different equations and lots of different formulas. It is a really good idea as I've done here, to make those little notes in your working. So jot down next to the equations what you're doing to manipulate them, making sure that you're updating those delta H values, going through this process here of cancelling out the unwanted chemicals. All of this in your working will keep you right and make sure that when you get to that final addition that you do it correctly. And what it's also going to do is it's going to show the marker that you understand the process that you're working through and what you need to do to these equations in order to get to your final answer. So really important, as always, that you do show the working and your thought process as you're working through these types of questions. Okay, you will find that their questions on this calculation are all very similar. When you start working through some examples today, you'll hopefully start to notice that. So once you get the hang of the process, it should become a little bit more straightforward, but it's quite a lot to get your head around at first. So let's have a look at another example, just to see if we can work through another one together. Okay, so here's your second example. Again, we've been given an equation at the start, so B2H6 plus 3O2, changing to B2O3 plus 3H2O. And again, it says use the data below to calculate the enthalpy change in kilojoules per mole for the above reaction. And we've got three equations that we're going to use and three delta H values. Sometimes you get a different number of equations. It just depends how many are needed for you to construct the target equation. So most of the time it'll be three. Some questions you'll only need two. The odd question you might have four equations to work with, but three is generally what you end up with. Okay, so we're going to use the same kind of terminology. So we've got our target equation at the top, equation 1, equation 2, equation 3 for the ones we're going to manipulate. And we're working through the same process, okay? So we're going to start by thinking about how we change these equations in order to construct our target equation. And then after that, we're going to change the delta H values and then ultimately use those delta H values to work out the delta H for the target reaction. Okay, so having a look at equation 1, boron and hydrogen don't appear in our target equation. So what we're interested in for equation 1 is the B2H6 on the product side of equation 1. But in our target equation, this is on the left-hand side, the reactant side. We've got the right number of moles because we only need 1 mole of it, but it's on the wrong side. So we're going to have to reverse equation 1 to put that on the correct side. And we'll do the same thing with the delta H. So this is going to become minus 36. Okay, looking on to equation 2. So again, hydrogen's not part of our target. Oxygen is. It's up here on the reactant side. So the oxygen here is in the correct place. It's not the number of moles we're looking for. But looking to equation 3, we do have some more oxygen down here that might help us get up to this number of moles. So we're not too concerned about oxygen from this equation because we have another equation with oxygen that will help sort that out. But what we do need to focus on with equation 2 is the water. So in the target equation, we need 3 moles of water on the product side. And in equation 2, this is the only place that water appears in all of these equations. And we've only got 1 mole. So we're going to have to multiply all of equation 2 by 3 in order to get those 3 moles of water. So that will change how much oxygen we've got as well, which might help us get to this goal. But we do have the other equation to help with that as well. So don't worry about the oxygen. Focus on the chemical that only appears in that one equation. That's our priority. That's what we have to get in the right place with the right number of moles. And anything else will sort itself out. So equation 2, we're going to multiply by 3, and we'll do the same thing with the delta H value. Looking at equation 3, so boron's not part of our equation. There's the oxygen that's going to go together with equation 2's oxygen. But our priority for equation 3 is the B2O3. So that's the only place this appears. And it's in exactly the right place. Exactly the right number of moles is what we need for our target equation. So 1 mole and on the right hand side. So we're going to leave equation 3 exactly as it appears. We're not going to change that at all. Otherwise we're going to not get the correct amount of B2O3. Okay, so I've just made these changes to the equations as we discussed on the previous slide. So equation 1 has been reversed, which now puts B2H6 in the correct place. And we've reversed the sign of the delta H, so making that negative. Equation 2 has been multiplied by 3, so everything in the equation multiplied by 3. And also the delta H value is now multiplied by 3. And we were doing that in order to get our 3H2O on the right hand side. And equation 3 we left exactly as it was because it gave us B2O3 exactly where we needed it. So that delta H value has just stayed the same. Okay, so before we add these values together, let's just double check we've done this correctly. So see anything that doesn't appear in our target equation, can we cancel it out? So starting with 2b, this is on the right hand side of equation 1, and we also have 2b on the left hand side of equation 3. So these two are going to cancel each other out perfectly. Also in equation 1 we've got 3H2, which does not appear up here, and in equation 2 we've got 3H2 on the left hand side. So both of these are going to cancel each other out as well. And that should leave us with our target equation. So if we just double check, we've got our B2H6 on the left hand side. We needed 3O2 on the left, which we've got. If we add these together, we've got 1.5 O2 from each of these equations. On the right hand side, we needed B2O3 and then 3H2O. So we've double checked that everything else cancels out and we've got exactly the target equation that we were looking for. So now, again, all we need to do at the very end is just add up all of our delta H values. So this time we're adding, these are all negative numbers, so it's negative 36 plus negative 858 plus negative 1274, which has given us negative 2186 kilojoules per mole. Okay, so you can see this equation, we just went through the exact same process as the previous equation, the previous question, sorry. Both calculations are very similar, it's the same method, same process. It's just different equations and different chemicals that you're working with and different delta H values. Okay, so what you can do, if you want some more worked examples than the two that we've gone through in this video, you can pause the video here, or actually just watch it after this video because we're nearly finished. There's a link here to a video on YouTube which takes you through lots of other examples of this calculation. So if you want a little bit more practice with it before you try any on your own, then I would suggest you watch the video and try a few more. Otherwise, if you're feeling quite confident about the kind of method, the process of these calculations, then that is Hess's Law really finished. That's chemical energy finished, the topic that we've been working on. So what you will have the chance to do in the next lesson, after you've had your little break, is do some practice on your own first of all. So with this Hess's Law calculation that we've done today, there's some booklet questions you can work through and just try the method for yourself. But what we'll also do just towards the end of our time in the lesson today is we're going to get together on Teams and work through some questions using the online whiteboards. So if you have any questions, if there's something that, you know, you've tried some examples and you're getting a little bit stuck with it, you will have that opportunity in the live session where you can ask for some help, and we'll go through some examples with you then as well. Okay, hopefully you've enjoyed the chemical energy topic, you've enjoyed this lesson today so far, and myself or Mr. Shepherd will see you towards the end of the lesson today for your live session. Okay, anything you need in the meantime, any questions you have, please post a comment on Teams or messages on Show My Homework or email, and we'll be happy to help you there. Otherwise, enjoy the rest of your learning, and we will hopefully be seeing you back in school next week. Bye.